Hi, guys, and welcome back to another episode of Women in Math and STEM, where our mission is to reach out to as many professionals, aspiring professionals, students, whatever you name it. We try to reach out to them, essentially support the initiative of bringing more women and young girls into the STEM field. So, with that being said, as always, feel free to open up the description or transcript to better follow along, and I hope you enjoyed this episode. Hello, and thank you so much for being able to make it to this episode today and speak with me. Just to sort of start off, do you mind introducing yourself as well as walking us through your math journey?
Yes, sure. First of all, it's a pleasure for me to be talking with you today. My name is Annalisa Quaini. I am a professor of mathematics at the University of Houston. And my math journey has started early because I've always actually liked math and science as a kid. I did all of my schooling in Italy. That's where I am from. I'm Italian. And I chose the more scientific high school, so where I had more math and physics than other disciplines. And after that, I was still interested in math, but I wanted to do something more practical. I didn't want necessarily to become a math teacher or something like that, which I ended up becoming, but anyway. And so I chose aerospace engineering for college, right? And so that's what I did. I went to the Politecnico di Milano in Italy. At the time, engineering was 5 years. So you would get bachelor and master together. You couldn't stop before. And the last 2 years, which would correspond to the master, actually, you could choose certain classes. And I took all the classes that were in computational fluid dynamics. So there is really a discipline at the boundary between aerospace engineering and applied and computational mathematics. And that's what led me to a PhD in computational mathematics. And that was in Switzerland at the École Polytechnique Fédérale de Lausanne. That's where I got a PhD position. After that, I joined the math department at the University of Houston as a postdoc for a couple of years before they gave me a job as an assistant professor, and then I continued my career there. So now it's 16 years that I am at the University of Houston, so a long time, and I am full professor. So I'm like that will be the last ladder, the last, part of the academic career. Yes.
Wow, that honestly sounds really amazing. I was just wondering, could you
Yes.
talk a little bit more about how maybe like your background in aerospace engineering in college influenced the way you approached or you viewed applied mathematics and computational science?
Yes, absolutely. Over the years, I have diversified the problems that I work on, but fluid dynamics remain very much the core of what I do. So, and to give you an idea, fluid dynamics is a really broad area, right? So, just to give you an example, right? As a PhD student, I could not choose the topic. I just had it was the position, the PhD position was financed by a grant uh, to study fluid structure interaction problems, so a specific kind of problem that arise in blood flow. So it's like, so blood is a fluid, right? And so that was the first kind of fluid that I simulated as a PhD student. So I worked with that kind of medical problems. And that's why I was hired at the University of Houston. The professor that hired me was collaborating with cardiologists at the medical center in Houston, which is one of the biggest, if not the biggest in the US. That's one type of fluid. Now, as you know, I've switched to atmospheric problems. The atmosphere is also a fluid. So you see really like two extremes, right? Blood and the atmosphere. So one is a liquid, the other one is a gas. And so it's really broad. But just to give you another example, right? One of the projects that has fascinated me is modeling crowds, how crowds moves, because you can look at a crowd as a fluid, like see how people move, can remind you of fluid. So that's why, I was saying I have diversified my projects because I like to explore new things, but really at the core, what I do, so many years later is still computational fluid dynamics.
That sounds really interesting. I was also just curious about like some of the biggest challenges when it comes to creating accurate and reliable like models for such complex systems like for fluids.
So the challenge there lies into striking a balance between accuracy and computational efficiency, right? So you can have a model that is very accurate, right? Because it accounts for so many different aspects of the problem that you're trying to simulate to understand. But if it's not computationally efficient, and by that I mean, maybe let me take a step back, right? In traditionally, we look at the world around us and we try to interpret it through mathematics, right? We write equations that describe natural phenomena like blood flow, like the flow of the atmosphere, and so on. Those equations are too complicated for us to find an exact solution, right? It's not like x minus 4 equal to 0, where you can say, well, x is equal to 4, right? It's too complicated for us to say what the solution is like. And so we use computers and algorithms. So algorithms to approximate the solution, and then computers are the machines that give us that approximated solution that we cannot find otherwise, right? So if your mathematical model is too complex, what can happen is that your computer will take too long to give you the approximated answer. That's what I mean. You need to find really a balance between accuracy and computational efficiency. If your model is too complex and then you have to wait years for the computer to give you an answer, that's not very practical, right? I cannot tell a medical doctor, come back in a month and I'll tell you what's happening with your patient, right? So that is the challenge.
I see. That makes a lot of sense. I was also just curious about sort of like zooming out how like computational science generally like serves or like improves scientific discovery or like innovation.
So I think that it is central, especially wherever you cannot perform experiments, right? And, practical experiments before computing machines, right? That's what drove scientific discovery, right? You run an experiment and then you try to understand what happened with your experiment, right? Um, but there are cases when experiments either cannot be done altogether. To give you an example, referring back to my work, I was telling you I've done simulations of crowds, and especially crowds under the effect of fear, stress, like panic induced by something that is happening, right? Be it a gunshot, fire, or something. As you can imagine, you cannot put a crowd in some arena and then start to shoot guns to see practically what can happen, right? So you have that's what a case when an experiment cannot be conducted. Or for example, so that is experiments cannot be conducted, or maybe they can, but it's just too expensive. And this is for this, I have an example that comes from my own work with other colleagues in my department. I have collaborated with a biomedical engineer, a professor of biomedical engineering at my university too, to design drug carriers. So these are nanoparticles that get injected into your bloodstream and carry the drug to the organ that needs it. And you can do experiments on these nanoparticles. They're just expensive, right? So if you manage to write down the model, write down an algorithm that approximates the solution to your model, and have the machine do the experiment instead of like doing it in practice, then it will save you money, right?
That makes a lot of sense. And also, I was just wondering how you balance like the technical aspect of your work, like finding the result, like finding like sort of like the solution to the problem versus like communicating that to like the people who are interested in it. So like maybe like the doctors or like the bioengineers you're working with.
Oh, yes. So a lot of my work is uh, actually doing, the math. That's like the majority of my time. Um, Talking with people that come from other disciplines. So I'm just talking, let me talk for the moment about talking with other professionals, and then let's talk about, communicating to just the general public, right? So it's it communicating with other professionals takes time. It is challenging, right? Because we've all been trained differently, and so you need to find a common ground from which you can, develop your project. And this can be easier or not, depending on the availability of such professional, right? For example, the professor of biomedical engineering with whom I collaborated, she was very much available. And actually, the building where her office is very close to mine. So for me, it was really easy to set up an appointment and say, like, there's something I don't understand here. Can we talk and try to figure out together? It's different with a medical doctor that is busy with patients. And so, there you kind of have more to rely on their schedule. As for the general public, this is something that I'm really getting to now. Um, I, and this is for different reasons, right? The first is that in the academic career, the first few years, you're still, let me say, under probation, right? You have 6 years where to produce your work. After these 6 years, you're going to be evaluated, and it's going to be decided whether you keep your job or not, basically. And so, I was busy trying to keep my job those first 6 years. And then also, so that one, I was trying to be practical and keeping my job, and so not using my time to communicate science outside the academic circle. And then also because I feel that before communicating with people that are not specialists, you need to become a specialist yourself. If you see what I'm saying, that I kind of wanted to become an expert before I could communicate, because these days there are so many people that are not experts that talk, and I didn't want to be that kind of person. I wanted to have the knowledge before I can actually communicate it effectively with people that are not scientists.
That makes a lot of sense. I was also just curious about sort of what challenges like computational science is currently being used to solve and maybe like what it should be used to like focus on, but also sort of where do you see computational science and applied mathematics maybe like a few years from now or like a decade into the future?
Oof, that's really hard. I don't know if I can. It's so hard for me to predict where things are going right now. You know, so computational modeling is used more and more in different disciplines. So, for example, as I told you, I started from aerospace engineering. Aviation has been modernized by modeling and simulations, right? So the planes that you take now when you fly, those have been perfected using computational modeling. But it's so that is a field where computations have been used for a long time. There are other fields like medicine, for example, where it's more recent to use computations. Um, the future, it's hard for me to predict. There are a lot of things up in the air. One is, as you know, machine learning and artificial intelligence, something that has exploded recently. And if you ask me about it like 5 years ago, no, maybe 5 years ago, I could sense that this was happening. But 10 years ago, I would have had no clue that this was coming, right? And in my field, right, what we are trying to do with that is to try to bypass human learning, like human understanding, by letting the machine learn for you, right? So, what we were saying earlier is that people have, um, for centuries, written mathematical models that explain what's happening around us, right? Now we say like, oh, whatever with the mathematical models. I'm collecting data. I feed the data to a machine and I let the machine do the thinking for me. So for someone that is trained like me, like trained in actually trying to understand what's happening, accepting what a machine spits out is hard. um, and so it's hard for me to understand where machine learning and artificial intelligence are going. And but that's gonna be with us for sure, uh, for a few years. And there is quantum computing. That is also something that people are talking about more and more. I don't have much knowledge about that. There are colleagues of mine that are, closer to that kind of computing, but that's certainly another thing for the future, whether it's near or far, I don't know, but it will be there. Yeah, so that's how far I can get, no farther than that.
I see. Also, I was just wondering, like, from your experience, what skills or qualities do you think are important for people who are interested or want to pursue computational modeling as a career?
So I would think that really you need strong foundations. Like, there is really not going around to going to college and studying hard, right? So strong foundations in math. If you want to do modeling, like, well, in general, right? Modeling, if you want to work with models that come from physical problems, like in my case, fluids, or it could be even any kind of natural phenomenon that you might be interested in. Then you also need to learn about the physics, obviously, right? And because so math, physics, whatever kind of physics you're interested in, whatever, but then you need also the computational aspect. So that doesn't mean that you need a degree in computer science on top of your math degree or something, but you do need to develop skills as a programmer, because especially in the early part, when you're thinking about an algorithms, you would have to implement it yourself. Then, if you want to take it to a bigger scale or something, you might hire someone to help you or collaborate with someone to help you to take it to a bigger scale or something. But initially, that job is on you. So, a lot of math, a lot of physics, a lot of programming, definitely.
Makes sense. And then I guess sort of to end off, I was just wondering what advice would you have or what resources would you recommend for high schoolers, but particularly young girls who are interested in pursuing such a career?
So I was thinking about this when you contacted me, and there are colleagues of mine that have done outreach to high schools. And so, what I would suggest, if your math or physics teacher or whatever is a proactive kind of person, ask them to look into faculty in nearby universities and see if they're interested in coming to your school and giving a talk. Just so that, you have um, you hear from a professional, right? From a mathematician, a computational scientist, or whatever it is about the research. And then you also have a person, right, where you can ask your questions to, right? Because sometimes, a job might seem cool and interesting until you find out what that person really does. For, you know, for probably 90%, 95% of, no, 90 of my working time, I'm sitting alone in front of a computer. So sure, it looks cool when you think about what you can do, but every day you're just sitting at the computer and typing, and thinking and typing. Uh, and so I think that would be actually a great experience if you can get an academic to come to your school. And I'm saying to ask your teacher, but you can do this also yourself. It's just that maybe, your teacher is more likely to get an answer from an academic because, people are busy but anyways, so, and, so that is one thing that I think you would enjoy. And then, when you get to college, so after high school, try to look into what people do at your college. What is the research? And a lot of us have some funding to do research with undergraduates. Yet high school students may not know enough to contribute to an academic project, but definitely as an undergrad, as you learn more, you can contribute to projects. So when you do get to college, try to expose yourself to research projects as much as you can.
Sounds good. And then I was also wondering if you had any.
Sorry,
Oh,
sorry, I
sorry.
don't want to cut you, but I forgot one important piece here
Oh,
because
of
you told
course.
me like to girls, right? And that's another thing that I suggest to girls is to build a community of other girls, and not just girls, but people that support girls to help you. We are still a minority, regardless of what they say. Women in science are still a minority. And so you need this group of people that supports you and you support them too, right? To carry you through the journey. That's super important. Build a community around you.
That sounds amazing. And I was also just going to say any like last words you would like to share or say to our audience.
I would be very happy if all of you join me in this, in this scientific endeavor of understanding what happens around us.
That's amazing. Thank you so much for coming today, sharing your story as well as your perspective. Thank you so much. It was amazing.
It's been my pleasure. Thank you.